Hello, this is James King and this is my Advanced Functions CCT. In this video you will learn about exponential equations and how to calculate instantaneous rate of change. My question is number 9 on page 508 of the textbook. The question reads, the current population of a town is decreasing at a rate of 1.8% per annum. The current population of the town is 12,000. The problem is then broken down into 3 parts. Part A states, write an equation that models the population of the town. This is a decay problem, so part of the equation will be 1 minus the rate of decay. Time is an exponent and the initial population must be included. It will be in the form of p at t equals pi times b minus d to the power of t. Next I substitute what I know into the equation. From the question I know the decrease rate of 1.8% per annum and initial population is 12,000. In all exponential decay questions, b is equal to 1. The equation can then be simplified to p at t equals 12,000 times 0.982 to the power of t. An important concept, although learned in grade 11, exponential equations, it is essential to solving the rest of the problem. The second part of the problem is focused on instantaneous rate of change. It says, estimate the instantaneous rate of change in the population 10 years from now. Essentially, this is asking to find IROC at t equals 10. I begin by mapping the steps out for solving an IROC question. First I determine the time, then I add and subtract 0.001 from t. I create a t-chart with t and p at t. I place the new values of t in the chart, substitute t into the equation, then I put p and t values into the chart. I use the IROC equation, which is y2 minus y1 over x2 minus x1, and I complete with a concluding sentence. Since the answer is an estimate, plus or minus 1/1000th will give an accurate instantaneous rate of change. I have organized this information into a chart with the variable of t and the dependent variable of p at t. To solve for p at t, substitute t for plus and minus 10 years and use a calculator. This method yields an answer of at 9.999 years there will be approximately 10,007 people, and at 10.001 years there will be about 10,006.6 people in the town. The equation for instantaneous rate of change, although taught in Unit 1, is the same equation as slope, which was taught in grade 9. Here, IROC at 10 years equals y2 minus y1 over x2 minus x1. This relation to slope can also be shown graphically. Here the curved line represents the graph for the exponential equation created in Part A, while the straight line is the tangent line. This means it touches the point at t equals 10 but does not cross. Therefore the slope of the curve equals the slope of the line. Now I substitute x's and y's for the corresponding numbers found in the table from earlier. Next I subtract both the top and then the bottom, and then I divide. The final step is to conclude. Minus 181.7 has been rounded down as you cannot have 0.7 of a person. Conclude with, therefore in 10 years the population of the town will be decreasing at a rate of 181 people per year. Note that the negative answer represents a decrease in people. Part C says to determine the instantaneous rate of change when the population is half its current population. To determine IROC at half the initial population, we must first determine what half the initial population is. Then we set the left side of the equation to that number and the rest of the equation stays as normal. We then bring 12,000 over and divide. We can log both sides after that because they have equivalent bases, and then we can divide the logs to get an answer. To begin, start by using the original statement, which gives an initial population of 12,000 and divide by 2. You get 6,000 people in the town. This represents p at t. Using the original equation created in step A, we can substitute 6,000 in as p at t. Now bring 12,000 over to the left and divide so that the left side of the equation is equal to 0.5. To solve for t, take the log of both sides of the equation. T goes out front on the right side. Now divide the logarithms one over the other. The answer of 38.1605 years is the time when the town is at half of its original population. It is important that we found the value for t as it is required in the instantaneous rate of change equation. Here the logs are able to be divided because they share the same base. The rest of the question is the same as in Part B but with different numbers. As in Part B, use plus and minus 1/1000th of the value of t for calculating the instantaneous rate of change. As was done in Part B, put your new values of t in a table for organization. Input the new values for t into the equation and solve. Place the answers that have just been found into the table to keep your answer organized. Now that we have our new values for p at t, we can set up the equation for IROC, as was done in Part B. Now, as was done with Part B, input the x and y values into the equation, subtract the top, then the bottom, and prepare to divide. Dividing should yield an answer of approximately minus 108.98, which can be rounded up to 109 because it's logically close enough. It is important to remember what the question was asking. It mentions both the instantaneous rate of change and half the initial population, so these should be addressed when concluding. Recognizing this, I have concluded with, when the town is at half its initial population, the population will decrease by 109 people per year. As someone interested in a career in medicine, I've decided to look into the profession of epidemiology and how it applies to instantaneous rate of change as well as exponential equations. Epidemiology is the division of medicine that deals with incidence, distribution, and control of diseases. This applies to the course of advanced functions, as exponential models on the spread of diseases can be created. Logarithms can be used to track a disease's progression over time, and based on the exponential equations created, instantaneous rates of change can be found. This is important as it can give projections on how fast the disease will spread in the future. Merry Christmas. I hope your family enjoyed watching this during their holidays, and thank you for giving me an assignment where I get to talk about how much I rock.